Hello, welcome back. The title of this lesson is called Acceleration in 2D and in 3D Space. So I'm excited to teach this because, in my opinion, I get to reveal something that we learn into physics, which doesn't at first seem to make sense, but I will make it make sense or have it make sense by the end of this lesson. And that's the idea of how does acceleration really work when you're dealing with 2 dimensions or 3-dimensional motion, right? So in the past, we've learned that acceleration along a straight line, when you can only go back and forth, acceleration is the change in velocity over time. So if you just think about driving in a car, if you're in a straight line motion, if the car speeds up, then we say it accelerates. So the acceleration is measuring how much the car is speeding up in the direction of motion. If you start braking on the car and you're slowing down, we call that a negative acceleration, and that acceleration just acts to slow the speed of the car down. Now, in one direction, it's very simple because you can only go this way or that way. So the velocity of the car and the acceleration, how much speeding up or slowing down, they're both in the same direction because there is only one direction. This way, well, I guess there's 2 directions, this way or that way. But it's only in one, basically, dimension. So the velocity and the acceleration have to be in the same direction. But when you have motion in 2 dimensions, like projectile motion, or in 3 dimensions, like in a space probe, then what we're going to find out in this lesson is that the velocity as a vector, arrow, and the acceleration as a vector arrow, because it has a direction also, in general, those 2 vectors are not going to be lined up in the same direction. I'm going to say that one more time because that's really important. In general, the velocity vector and the acceleration as a vector, when you draw them on the board, they will not be in the same direction. And the first time you look at this, you either understand it and you file it away, or like most of us, including me, you kind of ignore it for a while because it doesn't make total sense. When I draw the pictures on the board of which way the acceleration is acting and which way the velocity is pointing, they're not going to be lined up. And if you don't understand why, then it's easy to just ignore it because you can still solve a lot of problems without knowing the intricate details of that. But what I want to do, instead of making you wait some period of time so it finally sinks in, I want to get that in your brain here in the beginning. So what we're going to do is draw a lot of pictures describing the motion of an object, and then we're going to draw the acceleration of the object, and we're going to understand in our bones why those 2 arrows, why those vectors are not lined up, and how it makes total sense. And as we do that, I want you to have an image in your mind of something. Now, we're going to have a whole lesson on circular motion along a circle later, but we can still use the concepts here. Here I have just a plug. This is just a wall outlet, nothing special. All right, if I begin to spin this thing around, of course, it's kind of a weird, it's not like a straight line string here because it's a cord. But you see the idea here. If I spin it pretty fast, I can get it going into a circular motion. Now, if I'm doing a very careful job, the speed, if I could just measure the speed, is very constant going around this circle. I'm not speeding up or slowing down in my actual speed, but what is changing is the direction of motion is always changing. I'm going in a circle, so my direction is always changing. Now, in the beginning here, I said that the acceleration was measuring how the velocity changes with respect to time. That's what acceleration is, how much it changes with respect to time. But here's the punchline that I really need you to understand. When we measure the change in velocity, you can really get that change 2 different ways. One way to change velocity is just to speed up like we did before in the car, just accelerate, right? That's one way. That's going to change your velocity, right? Another way is to change the direction of motion. So you see, even though my speed going around this circle is not changing, my direction is always changing. And because of that, the velocity is always changing. So when we say that the acceleration is related to how much the velocity is changing, either it needs to be changing in speed or it needs to be changing in direction. So even though most people would look at this and say it's not accelerating because I'm not speeding up or slowing down, this thing is accelerating. This motion of this object at the end of this little cord here, it is accelerating. And it's accelerating because the direction of motion is always changing. So I want you to remember that in your mind because that is a core thing that we're to come back to. To get an acceleration, you can either get it by physically speeding up or slowing down, or by changing the motion, because either one of those produces a change in velocity, a change in speed or a change in direction. that produces a change in velocity, which is what we call acceleration. So what I want to do is put my little prop down for a second. We're going to come back to that. And I want to review a couple of things because we have to kind of like remember where we were so that I can continue the journey. So we're going to recall in one dimension because we have these equations that we've already basically used quite a bit, and we're going to extend them here in higher dimensions. So in one dimension, we defined the average velocity in the x direction because it was only one direction we were talking about. And we said it was x2 minus x1 over t2 minus t1. Now what this means, if I want to find the average velocity in only one direction, I just subtract the final position minus the initial position. That tells me how far I went, and then this is how long in seconds, and it's meters per second. You divide them, and you get an average velocity over that interval. And we have a shorthand way of writing that. We call it delta x divided by delta t. Change in the position divided by the change in the time. All right? Now this was called, I guess I'll write it down right underneath here. This was called average velocity. Only in one dimension, right? Now, we also talked about the idea of instantaneous velocity. In the x direction, we don't have the average anymore. We just have to call it in the x direction, and we said that it was the limit as delta t approaches 0 of delta x divided by delta t. And we went through this many times before. What we're doing is we're finding out how far the thing went divided by how long it took, but then we shrink the interval of time. We still go a very tiny distance in a very small amount of time. We get it small enough, we call it the instantaneous velocity at that point. So this was called the instantaneous velocity. Okay, so let me kind of like put those aside. All right, now what else have we learned? After we learned how to calculate the average velocity and the instantaneous velocity only in one dimension, then we moved on to acceleration. And we said that the acceleration in the x direction, the average acceleration in the x direction was, in words, it's the change in velocity over some time interval. So it's going to be some final velocity, v2 in the x direction minus v1 in the x direction, and then it's t2 minus t1. This is literally taking the final velocity minus the initial velocity in the x direction. That figures out how much it sped up or it slowed down, and you divide by the time it took. And the shorthand way we write this is delta v sub x over delta t. Now this is an average over some interval from initial to final. Okay, and we called this average acceleration. Right? I promise we're getting to the new stuff, but we can't go too fast because if you don't remember exactly what we've done before, then you don't know why what we're about to do makes total sense. Now, the instantaneous acceleration we can write in the same way as kind of what we did right here. We can say that it's the limit of delta t as delta t goes to 0 of delta v sub x divided by delta t. Now, what this means is that we see how fast the car speeds up, the final minus initial in the x direction, and we divide by the time. But then we let the time interval get very small, and so it becomes like an instantaneous acceleration at a specific point in time. And this was called the instantaneous acceleration. All right, making progress. So this is all in one dimension, and this makes total sense, and we've done all this before. We've solved problems with this and so on. Now, after we did the motion in one dimension with acceleration, then in the last lesson, we talked about what does velocity look like when we're not in one dimension anymore, we're in two dimensions and actually extensible to three dimensions. So we're going to move on. I'm going to say in 2D, but just so you know, it applies to 2D but also three dimensions where you have an x, y, and a z. So it's the same equation. Then we just talked about in the last lesson that the average velocity is now a vector quantity, and we don't put x direction anymore. This is the total average velocity, and in x and y directions kind of mixed together. And it's a final minus initial position, just like we did here over the time, but since it's in 2D space, we have to talk about vectors. Final position vector minus initial position vector. And we talked about how to subtract those vectors, and then we said final time minus initial time. So it's the change in position divided by the change in time, but they're just vector positions, and whenever you do that, you get a vector velocity. Now, the shorthand way of writing it is delta r, delta t. So we did this in the last lesson, right? And this we called average velocity. And we say that this is the average velocity in 2 dimensions. Now you can see where we're going. This is the average velocity. Last lesson, we already wrote down that the instantaneous velocity, again, we don't put x direction, we just say the instantaneous velocity is the limit as delta t approaches 0 of delta r as a vector. So the change in position divided by the change in time, we let the time get very, very small, and we call it the instantaneous velocity. So I can write this as instantaneous velocity. All right, now all of that stuff you really should have already been exposed to because I taught extensive lessons in that. We did everything in 1 dimension, understand the equations. Then we did velocity and position in 2 dimensions. Also, you can extend it to 3 dimensions. So now, here we take a breath and say, how do we handle acceleration? Well, we already know that acceleration is just the change in velocity. You can see it right here, divided by the change in time. In the instantaneous form, it's the same thing, but we just take the limit as the time interval goes to 0. So we can then talk intelligently about, in 2D, the acceleration. And the acceleration shouldn't come as a huge surprise. The average acceleration as a vector quantity is the final velocity, we call it v2, but it's now a vector, minus the initial velocity, we call it v1, but it's now a vector. And then we divide this by the final time minus the initial time. So it's literally the change in velocity divided by the change of time. And the way that we write that in shorthand way, change in velocity, change in time. But the difference is these velocities are now vectors. And you remember from the last lesson, vector has a direction and a magnitude. We're going to draw some pictures in a minute, but basically that tells you in general how the thing is moving. The velocity vector tells you at a snapshot of time how everything is moving. So now we have defined a new vector, and this new vector is called the acceleration vector, but it's calculated the same way as we did in the past. We just take the subtraction of the final minus initial velocity as vectors. That's the change in velocity divided by the change in time. This is the average acceleration over some interval of time between some initial and final position. So we call, or initial and final velocity. We call this the average acceleration, right? Now, what do you think the instantaneous acceleration is going to be? It's going to be exactly the same thing with the limit there. So we just now take the limit as delta t approaches 0 of what? Delta v as a vector divided by delta t. So same sort of thing. We just figure out how the velocity changes, final minus initial, as a vector, and then we divide by the time interval, but we let the time interval get very, 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 very small so that at an instant of time we say that this acceleration points in some direction and that this acceleration is measuring how the velocity is changing. It's called rates of change. So this is the instantaneous acceleration. All right? So after all of that, what have we done? We wrote down some equations. I could have just written them down. I could have just said, here you go. But we want to understand them. Where does this acceleration point in space? And I just told you the punchline in the beginning. It doesn't point in the same direction as the velocity. In one-dimensional motion, when you're only going along a line, pretend that you're at a stoplight in a car and you floor it. Then you accelerate. So your velocity is in this direction, but because I'm speeding up in the same direction, my acceleration vector is in the same exact direction. When you only have one-dimensional motion, the acceleration and the velocity have to be lined up because there's only one way you can go. But when a baseball flies through the air, when I take my little cord and I start flinging it around, the velocity can be pointing in one direction and the acceleration in general is pointing in a totally different direction. How can that be? That's what we want to unpack for the whole rest of the lesson. I want you to get a good understanding for why those two vectors don't line up. Because for this, it's important, but it's also important for lessons down the road to understand how the vectors behave, right? So here we have the vector form of the average acceleration. Here, the change in velocity vector divided by the change in time. And here we have the instantaneous acceleration. Same exact thing, but we let the time interval approach 0. So here we've been talking about the full vector equation of the acceleration. But we can also think about components of acceleration. Just like in the past, I told you that velocity, you can think of a horizontal velocity in the x direction and a vertical velocity direction, basically breaking up my motion into a vertical and a horizontal direction. That's how we handle all problems. For acceleration, the same thing is going to happen. We can be pointing an acceleration in some direction, but we can think of an x component of the acceleration and a y component of the acceleration, which act completely independently. And that's how we're going to handle acceleration too. So it all boils down to vectors point in whatever direction they point in, but we can always break the vectors into an x and a y component. And in 3 dimensions, also a z component. So the math remains the same. We just have one extra dimension if you handle 3-dimensional motion. So in terms of components of acceleration, what do the equations look like? Well, they look like exactly what you would expect them to look like. The average acceleration in the x direction, if you only look in the x direction, is going to be equal to how the velocity changes only in the x direction divided by delta t. Now, these are not vectors anymore because I'm only talking about the x direction, and I'm taking the change in velocity only in the x direction divided by the change in time. And I'm going to get only the x component of the acceleration, of the average acceleration here, all right? And then we also have the y component, the average acceleration in the y direction. And it's the change in velocity in the y direction divided by the change in time. So this makes sense, right? Because we know that the average acceleration is just the change in velocity divided by how long it takes to change in time. All I'm telling you is that the x component of the acceleration is the change in how the x component of the velocity changes with respect to time divided by the time interval. And the y component of the acceleration is just how much the y velocity changes, only the y direction, divided by the time interval. So the equations look the same. You can break it up into an x acceleration and a y acceleration. So these two equations are average acceleration. But of course, in component form, in x and y component form. If you had a z component, because you had 3-dimensional motion, you would have a z acceleration average, which would be the change in velocity in the z direction divided by the time interval. Now, we can write the instantaneous velocity for each of these, and we can just say the x component of the acceleration is the limit as delta t approaches 0 of the exact same thing, delta v x delta t. And then we can do the exact same thing right here. We can say that the y component of the acceleration, instantaneous, is delta t, goes to 0, delta v y delta t. All right? So basically, the bottom line is that we already know that the velocity of something is how its position changes with respect to time. And now we know that the acceleration of an object is how the velocity changes with respect to time. When you look at the full glory of the vector equation, it's how the velocity vector changes with respect to time. And you can make it instantaneous by letting the time interval shrink down. But you can think of an x and y component of acceleration, which will you can think of that x and y component being the acceleration vector in the x direction and then the y direction. But you can also calculate it by just looking at the x velocity motion and the y velocity motion and calculate them separately, and you can have the instantaneous values as well. Now, this is all great, but pictures really are going to save us here. We really need to get an understanding of how this works in terms of pictures. So we want to talk about some motion here. So I'm going to draw one little xy axis right here, and then right next door we're going to do the exact same thing. Something like this. So this is x, and this is y, and this is y, and this is x. All right, and just like we did in the last lesson, we're going to consider some sort of motion. So this is kind of like a semicircular arc, just for illustration purposes, right? And I'm going to do the same thing over here. So this is the path. Some path as I throw something in the air. Maybe it could be a rocket launch or something like this. We did the same thing in the last lesson. Now let's say that on this path right here is some point in time, and there's some position P1. So there's a ball or something, and it's right here at this time. And then a little bit later, it's at some new position, P sub 2. So it just kind of flies along a path like this. Now, in the last lesson, we learned a really, really, really important topic. We learned about the velocity. We talked about in 2 dimensions, the average velocity was the final position minus the initial position in vector form, change in position divided by change in time. And when we shrink the time interval down, we call it the instantaneous velocity at a point. And crucially, we learned in the last lesson that the instantaneous velocity is always what we call tangent to the position, tangent to the path. And tangent just means it touches at one spot. So if I can draw it, I'm probably not going to draw it right, but this is something tangent, I don't like the way that turned out because it looks like it's curved. Something like this. Still don't like that. Sorry about that. Something like this. So that's a straight line arrow that touches the actual trajectory path only in one spot. It just barely kisses it right down here. And we call this velocity at time 1 right here, at position number 1. This is the instantaneous velocity at point 1. And it's an arrow that is not curved. It's a straight line vector arrow. The length of the arrow represents how fast it's moving, and the direction, in other words, the angle, if I measured the angle to the horizontal, however many degrees, that would be at that moment in time, the direction and the speed of that object. That's the instantaneous velocity. Now, a little bit later on, of course, the path is bent over a little bit, so the instantaneous velocity is slanted in a slightly different direction, but it's still tangent to the path. So here is a vector velocity, instantaneous velocity at point 1, and a vector instantaneous velocity number 2. Now, I want to emphasize that in kind of this thought experiment, I'm considering the case when the speed doesn't change. So here it's going like 5 meters per second, and here it's going 5 meters per second. The only real difference is that it has moved, and so it has bent over and it's pointed in a different direction. If you take but the actual speed hasn't changed, the direction has changed. If you take my little hokey little demo here like this, at any 2 instants of time, because I'm trying to hold this thing at a constant speed, I'm still going around and around at so many centimeters per second or so many meters per second. The speed is not changing, but the direction is always changing. At any instant of time, it's always changing. But you gotta think about what's going on here. If I cut this, if I actually got scissors and cut the cord here, as I'm flinging it around like this, what's gonna happen? It's gonna fly off in some straight direction. We're gonna learn about this a little bit later, but basically objects always tend to move in straight line motion unless they're acted upon by an outside force. We're going to talk about that a lot later. I'm getting a little bit ahead of myself, but I think you would also you would all agree that if I cut the thing right now, cut the string, then this thing is going to fly away. How is it going to fly away? It's going to fly away on a path that's tangent, on a direction that's tangent to the original circular path. If I cut the string, like if there's a string here and I'm flinging it around, I cut it, then of course the thing is going to fly away in a straight line tangent path. If it was at this point and I cut it, it's going to fly away in a tangent path. So the velocity vector is telling you at that moment of time, if I cut the cord, that thing is going to sail in that direction because there's no more force acting on it anymore, right? Because the string is gone if I just cut it. Now, the planets that orbit the solar system, there's a force of gravity holding them there, pulling them in, and they're also going around like this. If I could suddenly cut the string of gravity or disintegrate the sun or just eliminate gravity, all the planets would start moving in straight line directions tangent to their orbits. They would just fly away in a straight line, just as we have done here. So hold that in the back of your mind because we're going to be talking a lot more about that in just a minute. But here is why the velocity is tangent. Here's why the velocity is tangent. That's the direction it would go if I cut the string at that point. Now what we want to do is we want to calculate the average acceleration between these 2 points, right? And we said that it's v2 vector minus v1 vector over t2 minus t1. That's what we just said before, right? The average acceleration is the change in velocity divided by the change in time. Now, as time moved on, the position of this thing moved from here to here, but then you might say to yourself, well, wait a minute, if I'm flinging this thing around in a circle, the speed hasn't changed, so there's no acceleration. But there has been something that changes. Yes, the speed is the same here as it is here, but what has changed is the direction has changed. Remember, a vector is the magnitude or how much of something you have, the speed in this case, and the direction. When we talked about vectors in the beginning, we talked about the difference between a scalar, which is just a number, like temperature or pressure, that's just a number, and a vector, which is like speed or velocity or magnetic field or electric field. Those are all vectors, okay? Because they have a strength and they have a direction. So yes, the speed or the strength, the length of these arrows are the same. So yeah, the speed is the same as the thing goes around. Just as I'm flinging this thing around, the speed is the same, but its direction has changed. So when we subtract them, when we subtract the vectors, final position minus initial, or final velocity minus initial velocity vector, the vector arithmetic takes into account any speed that has changed and also takes into account any direction that has changed. Because when we subtract vectors like this, these two vectors, even though they have the same length, they are not the same because they're in different directions to each other. So what I told you in the beginning is you can get an acceleration even if the speed is the same, just because the direction is changing. And that is something totally different and totally foreign than any of us think about, because we always think about driving a car in a straight line and we say we accelerate when we speed up, right? But I'm telling you that even if the speed is the same in my little circular motion, my direction is always changing. So when we ask ourselves, what is the change in velocity? Well, a change in direction of that velocity counts as a change in velocity. So it's different. It's pointed in a different direction. You need to start thinking about vectors being different if they're pointed in a different way, not just if they get bigger or smaller, but if they are pointed in another way. And this velocity vector is pointed differently than this one. So of course, when we subtract them, we're going to get some answer, because this, even though it's the same speed, the same length, is pointed in a different direction. All right, that's a bunch of talking. But let's get back down to business here. How do we subtract these? It's going to be V2 minus V1. So what we do is we say, all right, at position 1, I'm going to redraw what I have here. At position P1, I'm going to go ahead and draw my little straight line arrow, something like this. And this is V1. And then at P2, position 2, see if I can get it pretty close, something like this, P2, we're right here. And V2 was the one that goes tangent to the path like this. This one was V sub 2. So what we have to do to calculate the acceleration is V2 minus V1. How do we subtract vectors? Well, we have to add the negative of V1. So in order to make it negative V1, we have to keep the same orientation as V1, but we have to flip it around and make the arrow go down. That makes negative V1, and then we're going to place it over here and actually add the vectors. So when we flip the thing around and maintain the same orientation, it's going to point something like this. Something like this. So this vector here is negative V1. Because to make a vector, and that is not right, because I cannot draw angles right when I'm looking at this thing sideways. If I get in front of it, something like, it's going to look more like this. Yeah, that's pretty close. I mean, that's not exactly right. You kind of line it up like this, it's still not right. Let's do a good job. Let's try to do a better job. If we do something like this, it's going to be something like this. And this is negative V1. Okay, that's pretty close. So we take the same length, we flip the arrow around, and we put it head to tail. And I think I made this one just a little bit too long, something like that. All right, so if we want to take V2 minus V1, the first thing we have to do is flip around V1. We did that. And then we move the vectors head to tail. So there's a head of this vector and the tail of the other. And then this vector, now we get to draw the resultant, which is connecting the tail of one to the head of the other. So this right here, that is the answer to the problem. And this guy right here is V2 vector minus V1 vector. And notice that once we do that subtraction, all we have to do is divide by the change in time. This is just a number. Delta t is not a vector, it's just a change in time, which is a number. So when we take a vector and we multiply it or divide it by something, we just make it longer or shorter depending on what we're dividing by. We don't change the direction of anything. So this direction is the difference in the velocity vectors. When we divide by time, that's just going to make the acceleration longer or shorter. So for instance, I could just say that the acceleration vector might be a little bit longer or something like this. So I could say that this is the average acceleration as a vector, this blue arrow like this. The same direction as the red arrow, but either longer or shorter, depending on exactly how many nanoseconds or whatever it is you're dividing by in this case, because I'm just drawing a picture, but I know it's only going to get longer or shorter. But the actual numbers don't matter. What I'm trying to get you to understand is take a look at what's going on. The velocity vectors will always tangent to the path, but the acceleration vector is pointed nowhere near the same direction as what we have as far as our velocity vector. It's pointed toward the center of the circle. And so I'll come back to my little picture. We're going to have an entire lesson on circular motion. But I do want to bring this into it because this is going to make it much more understandable. As I fling this thing around, right, what we're saying is that the velocity, or the speed, I should say, going around the edge of that circle is the same. I'm not changing speed, but I am changing direction, so I must have an acceleration, because acceleration is the change in velocity vector divided by the change in time. But I'm not changing speed, but I am changing direction, so I therefore do have an acceleration that's happening. And that acceleration, according to that picture, is pointed kind of toward the center of the circular motion, right? So the thing that you need to realize is that we're going to get to this a little bit later, but when things accelerate, they can basically only accelerate if there's some force pushing them in the direction of the acceleration. When you're in the car and you floor it and you accelerate, you're experiencing a force in that direction that's causing the acceleration. It's called Newton's law. We're going to get into Newton's law later, but basically it just means that forces and acceleration always come in hand with each other, and you can't really have an acceleration without a force, right? You basically just can't. And so if I'm telling you that this thing is accelerating toward the center of the circle, then there must be some force in the same direction of that acceleration there. Now, if you look at what I'm doing when I'm actually spinning this around, and if you imagine doing it yourself, where's the force? The acceleration is happening toward the center of the circle. If it's here, it's this way. When the particle gets to this side of the circle, it's pointed this way. When the guy gets to the bottom, the acceleration is pointed always to the center of the circle. And I'm telling you that accelerations are always caused by forces in the direction of the acceleration. Where's the force coming from? Well, the force is coming from my hand. I'm pulling on this thing. So yes, I'm doing a little circular motion with my hand, but what I'm really doing is I'm pulling. When it's up at the top, I'm pulling down a little. When it gets over to the side, I'm pulling in a little. When it's to the bottom, I'm pulling up a little. Basically, this motion with my hand is I'm constantly pulling in to the center of the circle. And that is why the thing is accelerating, because the only way things can accelerate is if there's a force. And I'm pulling with my hand constantly toward the center of the circle. You can think of it this way. All objects want to go in a straight line. So if I cut the string and this thing just sails off, it would go in this direction. But we know that the thing curved so that it's going now in this direction. And later it would be going in this direction. And here it was going this direction. So things do not change direction unless there is some sort of force. And that means that there has to be some force pulling this way to make it curve like this, because things don't curve on their own. There has to be some kind of force doing it. And this acceleration here is just another way of talking about the force that must be there. We're going to find later that force and acceleration are directly related to each other. Force is actually equal to the mass times the acceleration of an object, and they're in the same direction. So at first it looks a little weird that you can have an acceleration pointing totally different to the velocity until you realize that anytime you see an acceleration, it's kind of like another way of representing or talking about the force that must be there, and there has to be a force acting on this ball, pulling it this way in order to curve the path. Because if there's no force going on, the path will never curve. The planets orbit in these ellipses because the force of gravity of the sun is constantly pulling in, causing the path to be curved. The object here is constantly going in a circle because my hand is constantly pulling toward the center of the circle. So at first it seems weird that you can have an acceleration totally different than the velocity until you start thinking of that acceleration being a proxy for a force, and you must be pulling down on the thing to get it to constantly curve its path. All right, I have a lot of words in my notes. I'm not going to write them all, but I want to make sure I say them all. I don't want to skip anything. So over here, I'm saying that as the ball moves, the speed is constant in this case, but the direction is changing. So when we subtract and find delta V, a change in speed, of course, counts as delta V, but a change in direction also counts as delta V. And that's why when we subtract these, we get an acceleration, even though the speed of the ball hasn't actually changed in my little example right here. But because the direction is changing, you do get an acceleration, and the direction of that acceleration must imply a force in the correct direction to change the motion the way that you think it should be changing, right? In this case, there has to be a force going down this way to curve the path, as we have talked about here. And then we said here in the delta V, that's a change in speed or a change in direction. We already said that. And then we said, if the speed is constant and the direction is changing, we have an acceleration toward the center of the circle. We talked about that. And then I say here, we learn later that acceleration only happens when force is applied in the direction of the acceleration. This force moves the object in a curved path. Think about a car, right? If you're in a turn then the car is accelerating. Even if you look at the speed on the inside of the car and it says 30 miles an hour or whatever, 20 kilometers per hour or something, and it doesn't change. If you're in that turn, and even if the speed is the same, as you go around that turn, you're accelerating. The speed has not changed, but the direction is changing. Because with vectors, it's magnitude and direction. So even if the magnitude of the speed is the same, the direction's changing, then you have a changing velocity, you have an acceleration, right? And that acceleration is going to be acting toward the center of the path. If you think about it being a car, and I'm just telling you, we're going to get to it later, that acceleration is going to come about because of a force that's acting. In the case of planets, the force is the force of gravity pulling toward the center. In the case of flinging this little thing around, the force is coming from my hand pulling to the center. In the case of a car, where is the force coming from? It's coming from the forces between the tire and the road. There has to be a force between a tire and the road to push the car in one direction to continue that curved path. If there was no friction, what would happen? Friction is the frictional force between the tire and the road is what's causing it. What would happen? Well, if you go onto an ice rink or a frozen lake and you do a hard turn, what's going to happen? There's no friction, so you're just going to keep going in a straight line, right? The frictional force has to be there because that's the force that turns the car. You turn the wheel, but it's really the frictional force with the road that does the work. All right? Almost done. I want to point out a couple of additional things before we wrap it up. So here we talked about the average acceleration. So here we had 2 points in time, right? Now, how do we get to the instantaneous acceleration? Well, we have to move these points of time closer together. So physically, point 1 would be here and point 2 would be a lot closer. So let's move point 1 and point 2 a little bit closer and see what happens. So if we have, an XY little, grid right here, or a little drawing here, and we say, all right, here is my path, something like this. And whereas before P1 was right here and P2 was over here, we can instead make P1 right here and maybe P2 a lot closer. And eventually we can make P1 and P2 right on top of each other to make an instantaneous acceleration. Now, we already know that P1 has a velocity vector tangent like this. This is V1 like this. And P2, at point number 2, we have some velocity vector tangent there as well. And then to make what we're trying to do, that the average acceleration is going to be V2 minus V1, the change in velocity over T2 minus T1, right? So what we have to do is we have to flip around V1 and then we have to put it head to tail. So we're going to flip it around. We're going to try to maintain the same orientation. It's going to be something like this. And this is going to be negative V1 because we're trying to subtract them, right? And so then what's going to happen is the actual acceleration is going to be something like this. So right here, what you're going to get is this is going to be V2 minus V1. That's the vector part of the top. We divide by time, and the actual acceleration will get bigger or smaller than this arrow, depending on what we divide by. But the direction is the exact same as we've been talking about. You don't know how many years I went without really knowing why the acceleration vector points to the center of the circle. I'm trying to get that out to you a little bit sooner here. All right. Now, if we continue this process, where we took a P1 and P2 far apart, we get it closer together. Notice it's still pointing toward the center of the circle. And if we get it closer and closer and closer and closer and basically make delta t go to 0, or as close to 0 as we can get, then we arrive at what we call the instantaneous acceleration. So instead of 2 separated points in time where we find the average acceleration over that initial and final state, we bring them close together so that they're essentially on top of each other. We call that the instantaneous acceleration. So that's what we need to draw next. So what we're going to do is draw in that little XY grid right here, or XY coordinate system, like this. We're going to do the same sort of thing where I go up, 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 and away. All right? And then basically we're going to say, here's P1, point P1. And P2 was over here, and then we did the vector, arithmetic, and then we got it closer and closer and closer and closer, and now P2 is essentially on top of P1. Then what's going to actually happen? Well, the instantaneous velocity is going to look something like this. Like this, it's always tangent to the path like this. And then what's going to happen is the instantaneous acceleration is going to be pointed toward the center. I'm just going to draw it something like this. And this guy is, where do I want to write it? I guess I'll do it right here. This is a vector, like this. So you see what's going on. The velocity is telling you what would happen if I cut the force that has to be acting right here. It's going to sail off in the straight direction. That is the velocity vector. It's telling you the direction of motion. If there's no extra forces doing anything, that's what it would do. But of course, there has to be a force here in the direction of this acceleration because the path is obviously being curved. And so this acceleration has to be acting toward the center of this curving. Now, this is not an exact circle, so what I've drawn on the board. So the direction of the acceleration is not exactly 90 degrees to the velocity, but if the motion is exactly circular, then the acceleration is literally 90 degrees to the direction of motion. And if the path is something else other than a circle, but just gently curved, then the acceleration can be skewed one way or another, but it's still going to, in general, point sort of toward the center of this curving going on here. But what I wanted to point your attention to is that this velocity is pointing in this direction, but we can think of components of velocity. What you do is you draw a little right triangle here on top of this, and you have something like this. And you can say that this is v in the y direction, and this is v in the x direction. So you can think of any velocity as being an x component of this velocity going horizontal and a y component which is only going vertical. And you can do the exact same thing with acceleration, right? You can think of it as being an x component and a y component, something like this, right? And what you can say is that down here, this is the x component right here, and then this right here is the y component, a sub y, and then, I guess I should have kept my little arrow right here. The actual vector is the arrow that's pointing in kind of like in the direction that we had drawn on the board right here. So I want you to start thinking about in terms of components. The velocity vectors pointing in some direction has an x component and a y component that vectorially add together to give me the velocity vector you have. The acceleration is also a vector. It's pointed towards the kind of the center of this curved path. There must be a force acting in that direction of acceleration to make that happen, but it also has an x component pointed this way horizontally and a y component, which in this case is actually pointed down. You can see that the arrow must be pointed down because the arrow's down here, where this one is over to the right and up. This one has to be down like this. So let me kind of draw these arrows a little better because we are going to talk about that a little bit more. So I can kind of like shade this and shade this something like this. All right, why am I doing all of this? Because this is the instantaneous velocity or instantaneous acceleration. We call it like this. We can say it's the limit of delta t approaching 0 of delta v over delta t. So it's the change of velocity divided by the change in time. Let the time interval approach 0. So we let the initial and final state be far apart, finally let them be on top of each other, and then we define an instantaneous velocity and an instantaneous acceleration. And I'm going to circle back to what I said in the beginning of the lesson. In general, the acceleration and the velocity vectors are not in the same direction. They're only in the same direction for sure if you're going in a straight line path and I'm accelerating in the direction of motion. But in this case, I'm not accelerating in the direction of motion because I'm going this way and I'm actually have to have some force pulling the path down, so there has to be an acceleration acting in a different direction than the velocity. But I wanted to start the lesson off by showing you how it makes sense. But now I'm going to blow your mind a little bit more and tell you that if you look at the components of acceleration and the components of velocity, everything makes sense the way you would expect it to. So over here we have point P1, these are the components of everything, but let's go down the way and let's just take some point in time later over here. And let me kind of, actually I think I'm going to do it, I'm going to extend the path like this, and I think what I'm going to do is I'm going to call P2 somewhere right around here, right? So what would be going on in this situation down the way? Well, there has to be some tangent velocity like this, call it V2. So it obviously changed directions. Why did it change direction? Because there has to be a force in the direction of the acceleration to bend it over like that. And there is an x and a y component of velocity right here as well. Right? So right here, this is v in the y direction and this is v in the x direction, and they add up vectorially to give you v2, right? So notice what's going on here. In the initial state, the x component was this big, but in the final state, the x component got bigger. In the initial state, the y component was pretty big, but in the final state, the y component got smaller. Do you see what happened? The length of this vector is the same, or I'm trying to draw it the same as this. That length of that vector, is related to, or it is the same thing as the speed of the object. When I'm spinning this thing in a circle, the speed, the absolute speed going around is the same. But the direction is, of course, different. Why is the direction different from here to here? Well, it's because the x component got larger and the y component got smaller. So when the x component gets bigger, the thing has to bend over and have more motion in the x direction and less motion in the y direction. So as the object goes around the circle, around any kind of curved path, the components are always changing. The x component is growing larger and then smaller again, and the y component is growing larger and then smaller again as the thing goes around to make the total length of the thing the same speed going around the circle. But behind the scenes, if you could put glasses on and look at the components of the velocity vector, you would see that even though the speed is exactly the same, the x component is constantly changing bigger and smaller, and the y component is constantly changing bigger or smaller, just as they have changed here. Now, here is what we now try to tie things back to what we have learned from before. We already know what acceleration means, right? When we look at the units of velocity, or speed, it's meters per second. But acceleration, if I can do acceleration right, is meters per second, which is meters per second squared. That's where the squared comes from. It's meters per second per second. Acceleration is how many meters per second am I gaining every single second. So it's like, whereas velocity is how far I'm going every second, acceleration is how much I'm speeding up every second. Or if you're decelerating, it's how much am I slowing down every second. So it's the rate of change of the velocity. But if I look at the x component, it got bigger. So how, in other words, I sped up in the x direction because this arrow is longer in the x direction. How did that happen? Well, it's because I have an x component of the acceleration pushing in this direction and making the velocity get bigger. When we have a positive acceleration in a certain direction, then we increase the velocity in that direction. In the x direction, I have this much velocity and I'm also accelerating in exactly the same direction. Therefore, the x velocity must be getting bigger, okay? Now, what's happening in the y direction? I have this much y velocity and it's getting smaller. Why? Well, notice that the y component of the acceleration is actually pointing completely opposite than the velocity. So I'm initially going up pretty fast, but I'm accelerating in the other way. That's the same as decelerating. When your velocity is going one way and your acceleration is going in kind of in a direction in the other way, it just means you're decelerating. So this kind of like acceleration in the opposite direction is changing my velocity and making it smaller. So when you look at the initial and the final state, the acceleration that's going on, even though at first glance it looks totally weird that the acceleration would be pointing to the center of the circle, when you look at the components, it makes sense because the x component has to make this x component get bigger and the y component has to make this y component get smaller because it's fighting it, right? And so at every moment of time, the acceleration is pointing in a different direction than the velocity, but the components, if you break everything up into an x and y component, everything makes sense. In the x direction, you must have an acceleration to make that velocity bigger or smaller. In the y direction, then the y component of the acceleration must act to make that velocity bigger or smaller. So again, just circling back to the beginning, when you first look at circular motion or velocity and acceleration in two-dimensional space, it looks completely weird that acceleration can be acting in a direction totally different than my velocity because we think that we increase velocity, that means we have an acceleration. They have to be in the same direction, but actually, it's acting this way. You can think of it a couple of ways. Because acceleration is a proxy for a force. We're going to learn later it's related to a force, and there must be a force there to curve this path. But also, if you break this acceleration into components, the components make perfect sense. X component of acceleration makes the x velocity bigger, and the x component of acceleration is fighting this one, which makes the y component smaller. And as the thing goes around the circle, wherever its acceleration is pointing is such that if you were to break the acceleration up into x and y, it would act on the x and y velocity directions to move the ball to the next state. And then you would have another acceleration, you would break it up, and it would move the x and y components of velocity into the next state. And as we go around the circle, that process is happening over and over and over again. That actually is the punchline of this whole thing. to show you why the acceleration vector points differently than velocity, and to show you that when you break it into components, it acts exactly as you would expect it to, component by component. And now you can see the power of breaking things into components. When we have a curved path, it's hard to analyze, but by breaking it into x and y, we can make sense of it. All right, I have a bunch of stuff at the end of my notes, but I think it's mostly regurgitating what I've already said. These two velocities, v1 and v2, v1 is not equal as a vector to v2. Yes, the speeds are the same, the lengths of the arrows are the same, but the directions are different, so they're different vectors, right? But we can say that the speed of v1 is equal to the speed of v2. When we put these bars, these look like absolute value bars. What they mean is the length of the vector. So we're saying the length of this vector is the same as the length of this one, which means the speed, like 5 meters per second, is the same. The vectors are not the same because the directions are different. The components are different, so they're different vectors, but their speeds are the same. And the reason they're not the same is because the directions are changed. The directions changed. This means change. The directions change between point 1 and point 2. All right, I have some notes here at the end. In general, acceleration is not in the same direction as velocity. I already said that. Think of the acceleration as related to a force, which we're going to learn about later, which pushes the path and changes the direction of the velocity as the thing goes around the path. I already said that. The components of the acceleration act on the components of the velocity in the expected way. In other words, they literally just push the components of the velocity in the directions you would expect. And two vectors, any two vectors are only equal if their components are equal. So yes, two vectors can both be 16 meters per second. But if they point in totally different directions, they're different because the x and y component of the vectors are totally different, even though the magnitude of the vectors could be the same. And then there's only one more drawing I want to make, and then we're going to wrap it up. It's a little bit of a rehash of what we have, but it's just drawn in a slightly different way. First, I'm going to draw kind of the same path here because we need to talk about the magnitude and the direction of the acceleration. So let me draw again, kind of speed this guy up here, the curved path. We can say, all right, here's P1, point number 1. We can say, all right, there's some velocity vector this way, call it V1. And we can say that there's some acceleration, which is obviously not going to be pointed in the same direction. It's sort of toward the center of this movement here. And we can talk about the components of this acceleration. So I'll draw the x and y components right here. And this guy will be the acceleration vector. And then I guess I'll do it in green here. This is going to be the x component of the acceleration. And then right here, this is the y component of the acceleration. All right. Now, how do we figure out, if this is the acceleration vector, the length of this vector? It's just the Pythagorean theorem. So what we can do is we can say the magnitude of A, or the length of it, is the square root of ax squared plus ay squared. So this is the Pythagorean theorem. Ax squared plus ay squared is equal to the magnitude of A, the length of this arrow squared. And when you take the square root to find the length of it in the magnitude of this acceleration, it's just the Pythagorean theorem here. And then we say that the angle that this acceleration acts is the inverse tangent of ay divided by ax. And so ay over ax, this is going to give you the tangent. Now, where is this angle in the picture? If you kind of draw something like this and kind of like put this guy right here. No, that's not right. Sorry about that. What you can do, when you think of trigonometry, it's always measured like this. It goes around like this, and then this is the angle theta. So it's measured, this is counterclockwise from the x-axis. So this would be the angle. And so it's the y component divided by the x component. That's just the definition of the tangent for a triangle. And then we're going to wrap it up with a couple little thought experiments. So I'm going to call this wrap up. You can always think about these things different ways, okay? Let's say that I have some initial velocity v1 and it's acting in this direction. And then what I do is I start accelerating this thing. How? Because I got to push on it somehow. But I start acting with some acceleration vector, which is acting in the direction of motion, So what's going to happen if this is just like straight line motion? If my acceleration is acting exactly in the direction of motion, it's going to behave exactly the way I think. I'm going to accelerate this and speed it up by delta v meters per second. So I start with so many meters per second, I accelerate it in the same direction of motion, so I increase its speed by so many more meters per second. And then what I find out is that the total new velocity is just the total new length of this arrow right here, which I call v2. So the punchline here is that when you have acceleration happening in the same direction as your velocity, then all you do is you increase the velocity. You don't change the direction of anything. If the acceleration is happening in the same direction of the velocity, it just makes it bigger in the same direction, and so the new velocity is acting in exactly the same direction. It's just bigger than it was before. This is what we typically think of as acceleration in a car. Straight line, accelerate, my new speed is now in the same, my new velocity is in the same direction, but with a larger magnitude. I'm going faster in the same direction. This is what we already know from the way we think about things. But in this case, we have now learned that what if we don't accelerate in the same direction as the speed I'm originally going? What if I'm originally going this direction, and I'm going to call it v1, like this. But now what I'm going to do is I'm going to then accelerate this thing perpendicular. I'm going to accelerate it, and I'm going to call this a. How do I accelerate it, by the way? Accelerations they go hand in hand with forces. So the only way I can accelerate this thing is by literally pushing on it somehow. Maybe I have a rocket thruster attached to my car on the side of the car pushing me sideways because I'm traveling this way, but I'm accelerating this way. What do you think is going to happen? If I start pushing on the car, then I'm not going to speed up or slow down the car. I'm just going to change the direction of the car. That's all I'm going to do. So what's going to end up happening if I accelerate it in this direction is now I'm going to be now traveling at a slightly different direction. And this right here is the change in the velocity. I change the velocity from initially pointing this way to initially pointing this way, and this is now v sub 2. Right? So this is an acceleration perpendicular to a velocity. So I guess I just wanted to draw one more picture to kind of get you comfortable with this idea, because in the beginning we think of acceleration only speeding up or slowing down, and that's because we only did one-dimensional motion. If you do accelerate in the same direction as your velocity, then all you do is increase the speed, and your new speed is in the same direction as your old speed, but it's just bigger and it's pointed the same way. So these vectors are lined up in the same direction. This is what we've done in the past. But if your velocity is pointing in a certain direction and you accelerate it out of the direction in a different way, in a different direction than the path of your travel, then it's not going to speed up or slow down this thing. It's just going to change its direction. And that is a change in velocity in terms of a vector, because when we think about the change of a velocity vector, it can be a change in speed, but it can also be a change in direction. So what's going to happen is this force that must be here is going to just push this thing down, and now your velocity is in a new direction. So this is why accelerations can and are usually in a different direction than velocities. If the velocity is changing directions all the time, there must be accelerations that are happening that are not in the same direction of the velocity, because accelerations and forces go hand in hand. You have to have forces to make accelerations happening. So if the path is changing, then you have to have forces. This is why accelerations are not lined up in general with velocities, because the only way velocities can change and move out of a straight line path and start curving is if there's forces involved. So this is why the accelerations happen this way. And when you first look at it in a book, it's very easy to cross your eyes and just get lost, because it doesn't make a lot of sense and it doesn't seem very important. But as we get deeper into this, you're going to understand that really understanding how these vectors work and why they work the way they do is very, very important. So I'd like you to watch this 2 times, maybe even 3 times, and then follow me on to the next lesson. We're finally going to start solving some practical problems involving position, velocity, and acceleration in 2-dimensional space.